Here's a classic question I bet you've thought about at some point. If you could just magically stop the Earth in its orbit, just freeze it in place, how long would it take for us to fall straight into the sun? It's a fantastic physics puzzle, and today we're going to solve it. Let's get into it.
Okay, so let's really picture the problem. Imagine you're out in space, right where the Earth is supposed to be, but there's no sideways motion, no orbital speed, nothing. You're just stopped. And then you let go. You just start falling toward the sun. Is that a quick trip? Does it take years? Let's find out.
Now, this isn't just some random question. This is a famous problem from a truly legendary and maybe a little infamous physics textbook by Irodov, Problem 1.203. It's one of those things that's kind of a rite of passage for physics students, mainly because it has this incredibly beautiful and clever solution.
At first glance, you might look at this and think, how on earth am I supposed to solve this with just basic physics? And honestly, that's a fair question, because it seems way more complicated than it looks.
Here's the real kicker. The force of gravity isn't constant. As our little object falls closer and closer to the sun's gravitational pull gets stronger and stronger and stronger. And a stronger force means a bigger acceleration. So the whole time it's falling, it's speeding up at an ever-increasing rate.
And this is the trap that so many people fall into. You remember from your high school physics class all those nice, clean equations for motion, right? The ones that use acceleration A? Well, the giant catch is that those only work when acceleration is constant. For our problem, it's changing every single second. So you can just throw those trusty old formulas right out the window. They're no help to us here. So if our normal toolkit doesn't work, what do? Are we stuck? Well, no, because the problem itself gives us this amazing subtle clue. It practically whispers the solution to us. See this little phrase buried right there in the text, making use of Kepler's laws? This isn't just a suggestion. This is Irodov telling us, hey, you're thinking about this the wrong way. Look at it from a different angle. This hint is a total game changer. It forces us to completely reframe the problem. We need to stop thinking about an object just falling in a straight line. The clue is pushing us to see this fall as a very, very special kind of orbit. I know. It sounds kind of bonkers, right? How can a straight line be an orbit? But stick with me here, because this is the mind-bending aha moment that cracks the whole problem wide open. So let's do a super quick refresh. Kepler's first law. It says that everything that orbits the sun, planets, asteroids, comets, you name it, travels in an ellipse, an oval shape, not a perfect circle. And the sun isn't at the center. It's at one of the two focus points inside that ellipse. All right, now let's play with that idea. Imagine you have one of those nice orbital ellipses, and you just squash it. You squeeze it from the sides, making it thinner and thinner and thinner still. What do you eventually get? If you take that squashing idea to its absolute mathematical limit, the ellipse becomes so thin that it's basically just a straight line. And that, right there, is the path our falling object is taking. There's a formal name for this. It's a degenerate ellipse. And our object's straight line fall into the sun is exactly 1/2 of this long, skinny, squashed flat orbit. The starting point is at one end, and the sun is sitting at the other. Okay, so now that we've wrapped our heads around this wild idea of a straight line orbit, we can bring in another one of Kepler's powerhouse laws to do all the mathematical heavy lifting for us. This is Kepler's third law, and it's awesome. It gives us a beautiful, simple relationship between how long an orbit takes, that's the period, t, and how big the orbit is. Specifically, it relates to something called the semi-major axis, which is just a fancy term for half of the longest diameter of the ellipse. So let's compare our two orbits, Earth's and our falling bodies. For Earth's orbit, which is almost a circle, the semi-major axis is just its distance from the sun. We'll call that r. But now look at our falling body. The entire length of its squashed-down orbit, the major axis, is r. So its semi-major axis is just half of that, r divided by 2. And this right here is the absolute key to the whole calculation. Because of that law, we can set up this wonderfully simple ratio. The period of our body squared over Earth period squared equals the semi-major axis of our body cubed over Earth's semi-major axis cubed. It looks a little intimidating, but now all we have to do is plug in the values we just figured out. All right, we have done all the hard conceptual work. We've reframed the problem, we've found the right tool for the job, and now it's time for the payoff. And the answer is just so neat. Wait,
One last crucial detail before we solve it. The number we're about to calculate, T sub body, is the period for the full degenerate orbit. That means falling into the sun, whipping around it, and going all the way back to the start. But the question only asks for the time it takes to fall in, so our final answer is going to be exactly half of that full period.
So let's run the numbers. The ratio of the semi-major axes is r/2 divided by r, which is just 1/2. We cube that and we get 1/8. So the full period of our body, T-body, is 1 over the square root of 8 years. And our fall time is half of that, which simplifies down to 1 over 4 times the square root of 2 years. So what does that actually work out to in, human terms? You punch that into a calculator and you get roughly 65 days. Just a little over 2 months. Wow, that's all it would take to fall into the sun from here.
And that's why this problem is so brilliant. We started with what looked like a horrible dynamics problem with changing forces and accelerations, something that would normally require calculus. But by using that little clue, we turned it on its head. It wasn't about dynamics anymore. It was a simple geometry problem about the shape of an orbit. That change in perspective made it easy.
It really makes you wonder, doesn't it? How many other problems out there, in physics or even just in life, that seem like a tough straight-line slog are actually just one piece of a bigger, more elegant orbit, if we could only find the right way to look at them.